Hello, I'm Seema and welcome to part 20 of the chapter States of Matter. Just before I started the video, I was watering this plant here. And why was I watering the plant? Because plants need to be watered. And why do plants need to be watered? Science tells us that I need to water the plant because the plant is going to use that water and then it is going to absorb the carbon dioxide from the atmosphere and it's going to use sunlight and then it's going to produce glucose molecules, which is food. So the plant is using that water to manufacture its food. I understood this by my knowledge of science. Then how does the plant use the carbon dioxide and the water? How does the water go into the leaves where it is manufactured? It is due to the presence of xylem and phloem tissue in the stem, and that is through which it is conducted, the water is conducted, and that is how through xylem the water goes up, and through phloem the food is distributed to the entire plant. So whatever facts we see in life, they are explained with the help of our knowledge of science. Since we have been doing the gas laws in the previous few videos, these were experimental facts, Charles, Boyle, or Gay-Lussac, or Avogadro. They derived relationships between pressure, volume, temperature, and number of moles. And these relationships were derived on the basis of their observations. Whatever they observed, they said, like Boyle said, that if you increase the pressure, volume goes down of a gas. If you increase the volume, the pressure goes down. Charles said that if you increase the volume, temperature goes up. If you increase the temperature, volume goes up. And if you decrease it, the opposite happens. That is, they are directly related. Volume and temperature are directly related. Then Gay-Lussac said that pressure and temperature are directly related. And Avogadro's, he said that volume and number of moles are directly related to each other. So these relationships were derived from experimental observations. But in order to understand why exactly was this happening, why do gases show these, why do gases follow these gas laws, a theory was made up and a theory or an explanation was thought up. This explanation was thought by three scientists who were Bernoulli, Maxwell, and Clausius. And the theory they gave, or the explanation they tried to understand gases at an atomic or a molecular level. Therefore, this theory was known as the kinetic molecular theory of gases. This theory tries to understand or explain the gases at a molecular level. So let us see what were the postulates of this theory. I've written down all the postulates and I'll be explaining each one. I've actually written down all of it here for you. The first postulate or the idea given was that gases consist of a large number of identical particles. These may be atoms or molecules that are so small and they are so far apart that the actual volume is negligible. They said, we know that air is present in this room. And if the molecules of air occupied a lot of space, then would it be possible for us to keep on stuffing the room with different things? I'm moving around in the room freely. There's furniture in the room. There's this board. There's this door. There's a table. And there's so much lying in the room. Could we have fitted all of that into the room if the molecules of air had occupied all the space? Obviously not. And we can go on stuffing the room with solids and liquids till we fill it up. And yet the air which is present is still there. It does not interfere with that. So what does it tell us about the air or the gas that is present inside this room? It is made up of molecules because all matter is made up of molecules. But these molecules that it is made up of are so far apart. They are so small that you could imagine that they hardly occupy any space. And that's the reason why we can keep stuffing the room with many other things, because the gas that is present, its molecules occupy almost negligible volume. They do not. It was assumed that the volume that they occupy is negligible, which is almost approximately equal to 0. Now this was an extreme actually, but yet the theory was that the volume of these molecules of a gas is negligible in comparison to the total volume of the gas. And what was the explanation? How did they explain this? They said, look, if we take a gas in a container with a piston, in a jar with a piston, and we start pushing the piston downwards, whatever gas is present, the molecules keep coming closer and closer and closer and closer, and the volume keeps decreasing, and you go on pressurizing, you go on pushing the piston inwards. The same molecules occupy much lesser volume and nothing happens. The high compressibility, how easily can you compress the molecules, shows that there's a lot of empty space between the molecules of gases. So this was the first postulate. The gases, they consist of molecules, and there are large spaces between these molecules, and the volume that these molecules occupy is negligible in comparison to the total volume of the gas. What was the second postulate of the theory? It said that there is no force of attraction between the particles at ordinary temperature and pressure. They assumed that there is no force of attraction. There can be no attraction between the molecules if at ordinary temperature and pressure conditions, the molecules of a gas are not attracted to each other. Have you ever noticed that if you take, let us say, a little liquid that falls over your table, let's say you're having coffee and at Starbucks, and you spill a little, and you still have time, and you're waiting for someone. So you start playing with the liquid. So what you do, you just plonk your finger into the liquid that is spilled there, and you start pulling. And when you pull your finger, or you try to trace a line on the table, you find the coffee, it starts moving with your finger. Why does it form? It traces a line as you keep moving and moving and moving your finger over the table, the water or the coffee or the liquid, it starts tracing a line along with your finger. Why do you think this happens? Water is a liquid, the molecules, whatever they were, when you plonked your finger into it, why did it start moving with your finger? Because the molecules of the liquid, they attract each other. So when you moved your finger, you were forcing some of the molecules to come with your finger. The other molecules were attracted, and they also moved along with the molecules that were touching your finger immediately. Right? So that is because there's attraction between the molecules of a liquid. But this is not seen in the case of a gas. What happens in the case of a gas? That if they attracted each other, the molecules, they should have moved together. But if I take this balloon and I burst it now, and the molecules of gas which are present inside the balloon, they would immediately expand and occupy the entire room. So, would it be possible if the molecules had some kind of an attraction? It wouldn't be possible. So that was the explanation that was given, that these molecules, there is no force of attraction between the molecules or the particles of gas at ordinary temperature and pressure conditions. Why did we say ordinary temperature and pressure? Because when the temperature is very low and the pressure is very high, that is when the molecules, they start interacting. That is when they do show attractions. But the kinetic molecular theory assumed that there is no interaction, there is no attraction between the molecules. And the explanation they gave was that gases expand and they occupy the space that is available to them. And this shows that gases, the particles of gases, they do not have any force of attraction. Let us come to the third postulate now. The particles of a gas are always in constant random motion. If they were at rest, they would have a definite shape. Understandable. The particles of a gas are constantly moving, and therefore a molecule is here at one moment and it goes to the other end in the next moment, and then it jumps. It is just bouncing here and there in a haphazard random motion. If it rested as the molecules of a liquid rest, or as the molecules of a solid rest, Then, in the case of liquids, the molecules do not rest permanently. It's a temporary rest. They are here and then they move slowly. But in solids, they just rest where they are. So if the molecules of gases rested, they would have turned into solids, which does not happen. So we say that particles of a gas, they are always in constant random motion. If they were at rest, they would have had a definite shape like solids. The fourth postulate reads that particles of a gas move in all directions in straight lines. They move in all directions. And these molecules, if you imagine these molecules, they here, it just moves here, then it goes here, then it goes here, then it goes here. It's random motion. There is no rule, nothing. It just moves where it wants. But they move in straight lines. And particles of a gas move in all directions and they move in straight lines. And during this random motion, they collide with each other. It's obvious when you have many children in a playground, or when you have, let us say, you have thermocol balls in a bottle, and you shake the bottle, the thermocol balls are randomly moving around. Or if you have marbles in a jar, and you shake the jar, what will happen? The marbles would move around and they would hit each other. So when they hit each other, they collide with each other. So particles of a gas move in all directions in straight lines. And during this random motion, they collide with each other. And would they just collide with each other? Would they not go and collide with the walls of the container too? So they go and hit the walls of the container. And when they hit the walls of that container, whatever it is, it's a balloon, the walls of a balloon. It may be the walls of a jar, the walls of a room. These bombardments are calculated as pressure. So it is these collisions with the walls of the container which exert pressure. So we say particles of a gas, they move in all directions in straight lines, and during this random motion, they collide with each other and with the walls of the container. Pressure is exerted by the gas as a result of these collisions. I have already taught you this in the previous videos, that pressure is exerted as a result of these collisions. Now we understand that these molecules which are colliding with each other, and they are colliding with the walls of the container, they are exerting pressure. But the question is, what happens when they collide with each other? Imagine if marbles are hitting each other, what would happen to their energies? And what would happen to the pressure? If the molecules are hitting each other and they lose energy when they hit each other, would the molecule that comes to the wall of the container, would it hit the wall with the same energy if it has lost some energy when it collided with another molecule? Now, if the molecules collided and they lost energy, what would happen? The molecules of gases would grow tired after their collisions. They're constantly moving, and when they're constantly moving and they're hitting each other and hitting the walls of the container, at some time they're going to grow tired, they're going to lose their energy, and they're going to settle down. And if they settle down, then they are no longer gases, because that's what we said. The molecules of gases have to be in random motion. So how was this explained? The fifth postulate explained this. They said that when these molecules, they collide, these collisions of the gas molecules are perfectly elastic. Now, what is an elastic collision? An elastic collision is one where two molecules, if they are colliding with each other, one is coming with one speed or one kinetic energy, the other comes with another speed and another kinetic energy, and they hit each other. There is an exchange of energy. One may gain energy, one may lose energy, but the amount of energy gained by the other one is equal to the amount of energy lost by the first one. So what happens? The total energy remains the same. There is no net loss of energy. There is only an exchange of energy. So this was explained by the fifth postulate. What did it say? That collisions of gas molecules are perfectly elastic. That is, the total energy of the molecules is constant. They may hit, they may gain energy, they may lose energy, but the total sum of the energy does not change. So they said that is the total energy of the molecule is constant. There may be an exchange of energy and individual energies may also change. The individual molecule, it is going and hitting, it was moving fast, it hit someone, oh, it got hurt, it's moving slowly now, but the other one is moving faster now. As slow as this gets, that the other one gets as much faster. So whatever kinetic energy one molecule lost, the other molecule gains an equal amount of kinetic energy, so that on the average, all the molecules still have the same kinetic energy. So these collisions, there may be an exchange of energy and individual energies may change, but the sum remains constant. If there was a loss of, how did they explain this? They said if, let us assume that there was a loss of kinetic energy, then the molecules would settle down, they would get tired, they would sit, and if they sat, they would turn into a liquid. They can't do that because they have to behave as gases, at least at that temperature and pressure. Under those temperature and pressure conditions, if a substance is behaving as a gas, the molecules cannot rest. The next postulate was that at any particular time, different particles, now how do you explain? Do all these molecules in a gas have the same energy? It's not possible. Even if they started initially with the same speed or the same kinetic energy, let us assume, when they collide with each other, there's an exchange of energy. And some molecules may gain energy, some molecules may lose energy, and now they have different energies. So in a gas, it is not possible for the molecules to have the same energy. The individual molecules will have different energies, but the sum of all, that is the average kinetic energy, remains the same. So this was the sixth postulate. Let me read what it says. It says that at any particular time, different particles have different speeds, and hence they have different kinetic energies. How was it explained? That as particles collide, speed changes. As they collide, the speed changes. One of them may gain energy, the other may lose speed. So even if they initially started with the same energy or the same speed, the collisions would disrupt this uniformity. Therefore, the molecules in a gas cannot have uniform speed. They can only have the same average speed. And therefore, it makes more sense to talk of the average speed or the average kinetic energy. So it says consequently speed changes, and consequently speed changes constantly, but average speed remains the same, and therefore it makes more sense to talk of average speed of the molecules instead of talking of the individual speeds of molecules. And if speed remains, the average speed is constant, then average kinetic energy of the molecules or the gas sample should also be constant. So we say if molecules have variable speeds, they should have variable kinetic energy. And if they have variable kinetic energy, each molecule has a different kinetic energy, then it makes more sense to talk of average kinetic energy. So under these circumstances, we can only talk of an average kinetic energy and not individual kinetic energies. It has been observed that average kinetic energy is directly proportional to the temperature. If you raise the temperature of a gas, the molecules on the average gain their kinetic energy. And when they gain, the average kinetic energy increases with increase of temperature. And if the kinetic energy increases, the molecules are going to hit the walls of the container with a greater force. And if they hit the walls of the container with a greater force, it means that the pressure increases. So as temperature increases, pressure increases. Which gas law does this indicate? This indicates what? It indicates the Gay-Lussac's law. Gay-Lussac's law says that temperature is directly proportional to pressure when volume and number of moles are constant. So the kinetic molecular theory could explain the gas laws very well. If you look at the second postulate, that there is no force of attraction between particles at ordinary temperature and pressure. It means temperature and pressure are constant and there is no force of attraction. Therefore, if you increase the volume, at ordinary temperature and pressure, there is no force of attraction between the particles. So if the gases can expand with the number of moles, the volume increases. If you have more gas, the volume increases. Which law is this? This is Avogadro's law. And Boyle's law tells us that if you increase the pressure, the volume decreases. So if the pressure here, let us say, increases, the pressure increases. When you increase the temperature, pressure increases when volume and number of moles were constant. But if you want the pressure to be constant, what should you do? Temperature is increasing, kinetic energy is increasing, but you do not want the pressure to change. Then what should you do? You should increase the volume. So if pressure and number of moles are constant, then as temperature increases, the volume should also increase. So in this way, we find that the gas laws can be understood with the help of the kinetic molecular theory of gases. But the problem came when we used the ideal gas equation. The ideal gas equation, and when we tried to understand that using the kinetic molecular theory, some faults of the theory, they came into our notice. We started noticing that there were some faults in this theory. So that will be our topic for the next video. If you found this video helpful, please give it a thumbs up and subscribe to my channel and recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.